Welcome to the makeup lecture for Wednesday, March 14th. Starting on the announcements page, you should have already received these by email, but just to make sure that we're all on the same page. So I extended the homework assignment deadline to Friday night. So if you're watching this today, the day I posted it, that would be tonight. And if you're still kind of struggling with, I know a lot of people have lots of things that are due right now. Since we have spring break next week, I'm happy to give you guys a little more flexibility, but that's up. And then I added another website that has access to data. And this website organizes census data and organizes it to where you can link to local, actually even local neighborhoods. So it's an interesting website if you're interested in exploring just aspects of different local neighborhoods, and you can come up with different hypotheses, thinking about comparing, if you want to think about comparing rural to urban areas, or even neighborhoods maybe within Denver, or there's all sorts of things you could do. So if you're still looking for ideas, this piton.org would be a website to take a look at. And just to remind you, we do have discussion boards up. So a couple of your classmates have posted requests for partners. If you have ideas for projects and you're still looking, that would be a place to go. And if you're struggling with finding a group, you can always shoot me an email and I can see if I can help out with that as well. So that is announcements and scheduling. Let's take a quick look there before we get into lecture. So let's see, your quiz 6 is due Friday. So that's the day I'm posting this lecture. So Friday the 16th. And that was over material from last week. So that is due either electronically. And if you've sent that to me, I am printing those and letting you know that I did receive them. So you should get an email back from me. Otherwise, if you've posted them, if you've given them to me in my mailbox, you're all good. And then next week is spring break. Yay. I'm hoping you guys have time to get a little bit of rest in. I know I'm playing some catch-up duties, but we all need a break, I know. And today we're going to talk about 8.1, which will transition us out of confidence intervals and into hypothesis testing. And then after the break, we'll go on and do a couple of other hypothesis test sections. Also after the break, just to remind you, project proposals are due the Wednesday after the break, so March 28th. And I am looking for about a page as detailed as you can give me on your design. And I'm looking for your hypotheses, what each of you in your group is going to be testing, how you're collecting your data. So as detailed as you can be is to your benefit, because then I can provide you some feedback and we can go back and forth. That way, any glitches that might be worked out ahead of time are worked out before you're graded on your project. So that would be to your benefit. All right, so lectures. So you should be able to get to your lecture. So this is 8.1, so you can download your slides. And I already have that up. So we're going to start into your lecture. So we just covered confidence intervals, and confidence intervals are focused on estimation. So we have a parameter and we're interested in estimating what that is based on a sample. Right? So we can't usually measure the entire population, or very rarely can we. The census is one attempt at doing that, but generally that's just not possible, so we need to estimate it. The other general area, large area of statistics is inferential statistics. Okay, so that's a chapter 1 review. And here we're interested in taking data and conducting a test, right? So in this chapter, we're going to learn to use an inferential method called a hypothesis test. Click this to bigger slides. And so the idea will be we're going to form a hypothesis that we're interested in testing. Okay, with a hypothesis test, kind of defines itself there. And we're going to collect data and use that data to see if there's evidence for a particular hypothesis. And then we're going to make decisions based on that data. And there are 3 main methods that people use for hypothesis testing. And one is the traditional method, which is what we're going to talk about today. One is the p-value method, and that will be mentioned in section 8.2, so that'll be after the break. And then the next method is through the use of a confidence interval. So test and confidence intervals are linked very tightly, and we'll get to that probably in a couple of sections. Actually, that may be chapter 9. So our main focus to start is going to be the traditional method and understanding what that means, and then the use of the p-value method first. Okay, so those will be in chapter 8. So traditional method, so just as a general overview. So the main goal in a lot of research studies is to collect data and then to support certain statements or predictions. Right, so what is a statistical hypothesis? So for us, a hypothesis is going to be a conjecture about a population parameter. Right? So a mean is equal to a certain value. Or if we have two populations, we might be interested in, are their means equal? So our hypotheses are specifically in correspondence to statements about their parameters. And this may or may not be true, and that's what we're trying to figure out. Do we have evidence to support a particular hypothesis, or to say that we don't have evidence to say that there is equality, say for two populations having the same mean? So as an example, say you are interested in whether you want to live in Denver or you want to live in Seattle, and you are going to base that on income, right? So one example might be to think about, well, is the mean income for a resident of Denver equal to the mean income for a resident of Seattle? So the population parameter we're talking about is then your mean income. You've got two populations you're comparing. So one population consists of residents of Denver, and the other consists of residents of Seattle. And so you want to know, is mu for Denver equal to mu for Seattle? Okay, so that's a hypothesis. Concerns two populations, and your parameter then is the mean. So that also should help you when you're thinking about your project. So those are the types of hypotheses you should be setting up. When we set up hypotheses, there are going to be two types. And this is going to be important because our tests are going to be set up to compare what we call a null hypothesis to an alternative hypothesis. And so a null hypothesis, it's null, okay, null meaning no difference. So it's the statistical hypothesis that states there's no difference between a parameter and a specific value, or that there's no difference between two parameters, right? So this is the thing that we start with. We say there's no difference, and then we're going to look for evidence that says that's not actually true. And our alternative hypothesis is generally what we're setting out to prove. Most of the time, people are looking for there to be a difference. I mean, scientists are generally wanting to show there's some difference. It tends to be more interesting. So our alternative hypothesis is the one where we state that there is a difference. So alternative hypothesis is a statistical hypothesis that states the existence of a difference between a parameter and a specific value, or that there's a difference between two parameters. Right? So if we connect back to our income example, so our null hypothesis was the one where the mean income, so mu for Denver, is equal to the mean income for Seattle. So mu Denver equals mu Seattle. Okay, so null. Null will always mean no difference. Whereas your alternative, so we were interested in whether they differed. Right? So our alternative is just that the mean income for Seattle is not equal to the mean income for Denver. Right? So it's as simple as that. Null will always be equal, and then the alternative will always be a difference. Okay, so that difference could be not equal, it could be greater than, it could be less than. And deciding which of those it is will depend on what you're interested in actually exploring. So just some tips going through this. we're going to tend to want to reject our null hypothesis. So we're going to start out actually assuming it's true, and then we're going to look for evidence to conclude that it's actually not true, so it's incorrect. So what we really want to do is to accept that alternative hypothesis. So if our null hypothesis is rejected, then we want to accept that that alternative hypothesis is true. Okay, hypothesis testing is set up in this way. And your null hypothesis, so null will always have your equal sign, right? So possibly a less than or greater than symbol, also depending on your alternative hypothesis, but it always has your equal sign. And then your alternative hypothesis has the range of values that are alternatives to the ones that are in your null. And it's the alternative that you are interested in showing. Okay, so we'll go through some examples to help you make that a little bit more firm. The null and the alternative are always stated together. And I'm going to go through a few examples. Sometimes we're going to be comparing two populations, and sometimes we may just be comparing a mean against a particular value. So examples might be, last semester I had a project where students had collected a sample of area students, and they were interested in seeing whether their vegetable consumption, their fruit consumption, their weightlifting practices, and their cardio practices reflected the governmental recommendations, right? So they had, I can't remember, like 2 servings of fruit, 3 servings of vegetables. I can't remember what the exact values were, but there are certain recommendations they had for amount of cardio and amount of weightlifting. Okay, so that would be their specific number. And what they tested was they collected their sample, and they wanted to know, is the mean value for area students for their fruit consumption, is it equal to the recommended value of 2 servings of fruit? Right, so that would be a null. So is it equal to? And they had hypothesized, I believe, that they thought it would be actually less. So their alternative was that there was a difference, and that the mean fruit consumption was less than 2. Right? So those would be 2 examples of a null and an alternative, so 2 hypotheses that would be paired together they were interested in comparing. So we've talked about 2 examples, so a difference. Okay, so the first one, the mean income, is going to be what we're going to call a 2-sided test. So we had equality in our null versus inequality in our alternative. Okay, so it's going to be two-tailed. The two-tailed is because we could have either the Denver income being larger or the Seattle income being larger. Right, so if we think of, maybe you looked at the difference. So the difference between those incomes, so mu Denver minus mu Seattle, that could either be too big, so large in the positive direction, or it could be too small, so it could be in magnitude large in the negative direction. Or we could have a right-tailed test. And so that would be, if you notice, all of our nulls are always equals. A right-tailed would be to say that we actually believe that the mean value is greater than your threshold. And then left-tailed would mean that we believe that the mean parameter or the mean value is actually less than. So the fruit example would fit into a left-tailed test. So what we're believing, or the students were interested in testing, was the null, that the mean fruit consumption for various students was equal to the recommended 2 servings of fruit, versus the alternative, that mean consumption was actually less than the recommended value of 2. So that would be less, and it's a left-tailed because if you imagine what you're testing against, so here's K. So where are you hypothesizing that true mu is? Well, so if it's left-tailed, you're hypothesizing that it's actually to the left of K. If it's right-tailed, you're hypothesizing it's actually to the right of K. And if it's two-tailed, you're saying, well, it's not equal to K, but it could actually be over here. or it could be over here. And what your test is going to do is figure out, okay, how far does your sample mean need to be away from K before you say, okay, that's too far away for that to just be random, for that to just be by chance. And just, something to maybe help you also as a quick way to remember this. If you view the less than and the greater than symbols as arrows, that actually points to the direction of the tail. So this is pointing right and that is pointing left. So that might kind of give you a good memory device also to help you remember that. All right, so some examples, and I'm underlining some keywords to help you think about how you're formulating your alternative. Okay, so keep in mind your null is always going to be equals. Okay, so we're going to go through, we're going to state your null and your alternative for each case. So here, the first example, a researcher thinks that if expectant mothers use vitamins, birth weight of babies will increase. Okay, so that's what they're hypothesizing. And we are given that the average birth weight of the population is 8.6 pounds. Right, so given no other treatments or conditions, average weight is equal to 8.6. So that gives us our null. So mu equals 8.6. And I know it's a mu because it's a weight, so it's continuous. The fact that they're hypothesizing there's an increase, so that's what they're saying, that the actual true mu is going to be larger. Okay, so increase tells me that my alternative is going to be that the true mu is going to be greater than 8.6. Okay, so increase is a keyword that tells me what direction my alternative is going to be. It's going to be right-tailed because I think it's larger than the 8.6. Right, so see what you think about this next one. I encourage you, so pause, take a minute, see if you can write out what your null is and what your alternative is. All right, so if you went about that, and I already underlined a keyword in there. Okay, so let's read through it. So engineer hypothesized that the mean number of defects can be decreased in a manufacturing process of compact disc by using robots instead of humans for certain tasks. The mean number of defective discs per 1,000 is 18. Right, so we're using 1,000 as our unit. So our null is always equals. So if I were to write this out, so for this, then my null would be mu equals 18. So that is my null. My alternative, so they are hypothesizing, so my alternative, that it's decreased. So they think mu is actually smaller than 18. Okay, so decreased is what tells me that that should be a left-tailed test. That's where I get the less than. So mu is less than 18. Right, so that's how I got that. All right, let's give this other one a try. And again, pause and then check back in. All right, so we have a psychologist feels that playing soft music during a test will change the results of the test. The psychologist is not sure whether the grades will be higher or lower, and in the past, the mean of the scores was 73. So, again, the null is always equals. So if I am writing this out for this one, then I am going to have for my null mu, it's going to be equal to, and that was 73. Okay, so that's without any other treatment. And then they are telling you that it will change. Okay, they didn't say increases, decreases, less than, greater than, just that it's different. And so that means Right, so I'm in a text editor, so not equals. So I'm going to use that exclamation point to denote that. So not equal to 73. And I know that it's not equals because I just know that it's different. They're just hypothesizing it will change. So it could be greater, it could be less than. All I know is that they're wanting to show that it's going to be different from 73. So a few other things. Generally, we are looking for evidence to support the alternative hypothesis, and it's very common. Scientists tend to look for differences as being more interesting. And so when we collect data, we have some claim that we're trying to make, and when we collect our data, we figure out then do we have evidence to support our claim. Right? So one of the other things you need to start looking for is what is the claim that your researcher is trying to prove. And since the alternative hypothesis is often what we're focusing on, a number of times you'll see this called the research hypothesis as well. So that's something to just be aware of. So a few other helpful indicators of what your alternative hypothesis should look like. So table 8.1 in your text gives you some identifying phrases to come up with, what would indicate that your alternative should be right-tailed. In other words, that you should be using greater than. If they are hypothesizing that something is greater than, above, higher than, longer than, bigger than, increased, all of those are indicating a right-tailed test. And it also gives you some terminology to show you that you have a left-tailed test versus a right-tailed test. So these might be helpful for you as you start learning how to take a word problem, take a statement from a scientific problem, and set up what your hypotheses are. So after you've stated your hypotheses, you will next need to figure out what your statistical test is. So we're going to learn a z-test and a t-test for a mean. And we will learn that for one sample, two sample where we have dependency. We'll also learn z-test for proportions for one sample and two sample. So depending on what the design is, you'll figure out your statistical test. You will either be given or you'll choose a level of significance. And then you will go about a plan for conducting your study. Right? So that's general once you've designed your hypotheses. So the statistical test is defined to be, so it uses your data obtained from your sample to make a decision about whether your null hypothesis should be rejected. Right? So we'll, like I said, talk about several statistical tests. And that decision tree that I had posted prior to the last lecture would be a good one for you to print out and maybe even start identifying either keywords or your formulas as we go through and learn your test and actually your confidence intervals along the way. So your test value is going to be the actual numeric value that we obtain from your statistical test. And the test value is going to be the value that helps us determine whether we're going to reject our null hypothesis or not. So this is some terminology that we're going to start using, and I'll explain as we go along. So we're going to take our statistical test, and when we conduct this test, there are a couple of errors that we could make. And I've got this 2x2 table set up, which is a pretty standard one that you'll see. The two types of errors, so highlighted, so these are key concepts for you. There's something called the type 1 error and a type 2 error. And this is, these are called that all over statistics. So very nondescript names, but they are type 1 and type 2 error. So if you think about what we're doing, in this table, okay, so your columns represent the state of truth. Okay, so you have your null, so the state of equality. So whatever you're testing is true, and you have a null result. So your null is either the truth of the situation, right? So omnipotous view of it, it's true, or it's wrong. Right? So there's really not equality. There's some kind of a difference that exists. And conducting your tests, so that's being represented in your rows. So you conduct your test, your data is going to lead to you rejecting your null or to you not rejecting your null. Within the table, there's 2 times where you made the correct decision. Right? So if your null is false and you reject it, yay, you did the right thing. If your null is actually true and you did not reject it, then again, you made the right decision. If, however, your null is true and you rejected it, you made what we call a type 1 error. Right? So that is to say there's actually no difference and we've just concluded that a difference exists. Right? If you, on the other hand, did not reject your null, so you're concluding there's no difference, when in fact there actually is, we call that a type 2 error. So type 1 and type 2 errors are 2 things that when statisticians design studies and design tests and think about sample size, that we balance against each other. And so one way to think about hypothesis testing is to set this up as somewhat of a legal trial. Right? So your text sets this up and tries to help you think through this in terms of evidence-based decision making. And so for us, so we've got the same 2x2 setup. And in a legal trial, so our null, so what we start out with is that your defendant is innocent. So it's innocent until proven guilty. And since we have a couple students who just were out for jury duty, they should appreciate this example. So you're null, innocent until proven guilty. Your alternative is that you're not innocent. Right? So null is equality. Your alternative is not equality. Right? So trying to set it up in that way. And in other words, not innocent means guilty. Right? So if you were the defendant, which of the errors would you consider to be worse and why? So it's something for you to think about. Other things to consider, you never prove whether the defendant really did or did not commit the crime. You're taking evidence and you're providing support for your conclusions. You're finding support for your hypotheses. And the idea in a trial, the idea in hypothesis testing is you want to know if the evidence or if the data is strong enough for you to say the alternative is true, right? To say that the defendant is not innocent, right? So it's the same thing with hypothesis testing. We're collecting data and we want to say at some point we have enough evidence to say the null is not true and that we can conclude that there is a difference. And the real question is, and this is where our sampling distributions come in, is that we want to know how large of a difference does there have to be, okay, or how much evidence does there have to be for us to reject that null hypothesis. Okay, so all of this is just based on your evidence. We're never actually able to conclude one way or the other. And for sure, we never conclude innocence. You can never conclude that the null is true. You start off under that scenario and you look for evidence to the contrary, but you never conclude innocence or not. You're just looking for evidence that says that you do not have innocence. A couple other key terms you're going to need. So significance level. So this is going to be the alpha. Actually, it's the same alpha we've been using for confidence intervals. And this is going to be the maximum probability you're going to allow of committing a type 1 error. So this is something we can set. So there is going to be a fixed level at which we're willing to reject your null when it's actually true. That alpha is going to be what we use to define our critical region, also called our rejection region. So we're going to come up with the values for our test statistic that say if you have a test value, so if you take your data, you you compute your statistical test. If that test value falls within the critical region, that is going to lead to a rejection. So hence the rejection region. So for our test, we'll define what this region looks like. We'll also then have the non-rejection region or the non-critical region, and these are going to be the values that if you have your test value within that region, you would not be rejecting your null hypothesis. And the critical value is the value of your test that separates those regions. So we'll learn how to, for each test, come up with that critical value. Your critical value is going to depend on a couple of things. It'll depend on what your alternative hypothesis looks like. So whether it's two-tailed, right-tailed, or left-tailed. It's also going to depend on what table you were using, right? So meaning what distribution you were using for your statistical test. And so we'll need to know, is it a Z table, is it a T table, or the other way of actually saying that would be, did we use a Z test or a T test? Right, so as we start thinking about how to set up our critical regions, we'll need to focus on whether we have a one-tailed test. And if that is the case, then we need to ask, right, is it a right-tailed or a left-tailed test? If it's a right-tailed test, then our critical region is going to be on the right side of the distribution. If it's a left-tailed test, then it's going to be on the left side of the distribution. Okay? If we have a two-tailed test, then we are going to have critical regions on both sides. So this is completely general, regardless of whether we had a Z or a T test. We'll do this for each test that we go through. Right, so we'll come back to this over and over again. And so just to give you a general representation of this, this would be how we would figure out on the critical region for a left-tailed test. We're going to come up with, so if this were a Z test, we would look in the Z table and find the value of Z that put an alpha percentage to the left of it. If we were doing a right-tailed test, we would find the value of Z that put alpha to the right of it. If we were doing a two-tailed test, then we split our alpha into the two tails and we figure out what value of, again, if it's Z, what value of Z fall here and here. And then our critical region would actually be everything to the left and everything to the right. Okay, so meaning that those two regions would represent everything that was too big and everything that was too small, right? And since it was a two-tailed test, that's saying, okay, these regions represent us being too far away from the value that we were testing. Right, so going through this, we are going to need to choose our alpha or our significance level. Okay, so that's what our alpha is. We need to know the distribution of our tests. Let's see, so the distribution of the test value indicates the shape of our distribution. So we'll be using, for this class, we use the Z or the T, so your standard normal or your T distribution, which means we're using table E or table F. And I'm going to go through and do some examples using the standard normal so you can see how that's done. And I do make a note here, actually at the bottom of the T table, and so I'll show you, maybe not this time, maybe the next time around, but if you notice at the bottom of the F table, it actually shows you a row that corresponds to critical values for the Z test. Right, so if you get comfortable enough and you want to start looking down and kind of playing with that, you can. So it's kind of a highlight of upcoming stuff. All right, so finding your critical values for specific alpha values. So we're going to assume we had a Z test. So I'm going to use my Z table, and that's table E from your text. Okay, the first thing you want to do is draw the figure for your test values. So if I'm doing a Z test, I'm going to draw my little bell-shaped curve. If you look at your alternative and it was left-tailed, then what you want to do is draw a hash mark to the left of your distribution. And then you want to shade in the area to the left to correspond to alpha. That's going to be your probability. If it's a right-tailed, you're going to do the opposite. So you're going to draw a little hash on the right, and you're going to have a probability of alpha to the right. If the test is two-tailed, you divide that alpha by 2. And so you're going to draw a hash on each side with alpha divided by 2 to the left of the one on the left and to the right of the one on the right. Okay. The next step is then, once you've represented where on that distribution you are, you look up in your table to figure out what that hash represents, right? What z value corresponds to that probability being to your left or your right. Right, so as an example, we're going to go through several. So if I have a z-test and I have a left-tailed test, so this would mean I have an alternative that looks something like mu is less than 0, say. Well, let's say I have an alpha of 0.005, right? So if that's the case, I've drawn my little bell-shaped curve. It's left, so I've drawn a mark to the left. I want 0.005 to the left of that mark. And so if I pull up my table, okay, so probabilities are in the center of the table. And if I look up 0.005 inside the table, that will give me the corresponding z value that has 0.005 under it. Right? So if you forget, that's the bottom figure tells you that is what it is giving you. So if I look, so it is right in here. So minus 2.5. And then it's in between 07 and 08. So minus 2.57, and I'm going to say 5. But again, I think your homework asked you to round up, so that would be minus 2.58. Let's see, so let's go back to those. So minus 2.575 or minus 2.58 if you round it up. All right, so if I had a right-tailed test, so alpha of 01, right? So that would mean that I am going to have a critical value to the right, so in the right tail, and I'm going to have 0.01 falling to the right of it. Okay, so if you're looking that up in your table, you need to remember that in the body of your table, that is the probability that is underneath. So that means if I am looking for something that falls here that has 01 above it, then there is 1 minus below it. So I need to look in my table to find 0.99. So I am going to look in here. And if I go down to my z table, 0.99. So this is my closest. So I have a critical value of 2.33, right? So my critical value for that, for a right-tailed test with alpha of 01, would be 2.33. All right, so hopefully that one was okay, but I'm going to switch over actually so I can type this out for you. All right, so the one that we just did was this. So I looked up 0.99 in my z table and ended up with a z of 2.33. All right, so we're going to do a number of other ones. So you get practice because you are going to be doing this over and over again. So just so you know, you need practice on it. All right, so your next slide. So we're going to do two-tailed test. And a left-tailed test, right-tailed, and a two-tailed. So you're going to get a number of ones to practice on. If you're feeling confident, pause this and go through practice on the 4, come back, and then you can check and see what you got. If you're feeling a little shaky, watch me go through a couple and then pause when you're comfortable and check yourself through wherever you at that point feel comfortable with. So two-tailed test. So for two-tailed, we split our alpha into two. And we are, so let's look at this one. So I am going to move that up. So if I have an alpha of 0.1, I need to find a critical value on each side of my distribution. So I'm going to need to split that alpha into two, right? And specifically, since I had an alpha of 0.1, I need a 0.05 over here and a 0.05 over here. Right, so I'm going to find this critical value first. So I'm going to look up 0.05 in my table. So if I look that up, let's see, some of you may have this memorized by now, maybe not. So 0.05, so that is right in between here. So that z-value is going to be a minus 1.6, and let's go with the 5, so if I round it up, right, so it's in between here. So a z-value of minus 1.65 has 0.0495 underneath it, right, or a minus 1.645 would be averaging right in between. So a minus 1.645, or actually we said 1.65. So that would be the value right here. Okay, so I also need the value on the top, which would have a 0.05 above it. And since the distribution is symmetric, then that's going to just be the positive of that. So I'm going to have a z of 1.65 positive on the top. All right. So left-tailed test. So for a left-tailed test, I need to put my critical value on the left. And I'm not doing any splitting because all of that alpha is going to be to the left of that. Okay, so I need to look up 0.2 in my z table, and that will give me the z value that has 0.2 underneath. So if I do that, let's see, so 0.2, since it's on the left, I know it's going to be negative. 0.2, so this is my closest, right? Yep. So that is a minus 0.8, and this is this column, so minus 0.84. So this is going to be minus 0.84. So my critical value, which is defining my critical region and non-critical region, is a minus 0.84. Right? Okay, so right-tailed test. So for a right-tailed test, that means my critical value is going to be on the right. So I need to find the value over here that puts alpha to the right of it. Right? So if alpha is 0.15, so I have 0.15 over here. That means 1 minus that is underneath. So 1 minus 0.15 or 0.85 is going to be underneath. And that's what I need to look up in my table, is what is underneath that bar. So 0.85. I know it's going to be positive because it's on the right. So if we go in here, 0.85, so it is, looks like this is the closest I'm going to get. Is that right? 0.8 away? No. This is, so that looks like it's a little bit closer. All right. Oh, this one is still closer. So I am going to pick a 1.04. So that is as close as I get. 1.04. And that is the closest value that would have 0.85 underneath it. And then finally, so a two-tailed test. Okay, so two-tailed means I need to find the two values that are on, okay, so each side, they are the values that split 0.09 in half. So 0.09 divided by 2 is 0.045. So I'm going to put 0.045 over here, 0.045 over here. Right, so I'm going to look up this one first. So I'm going to look up 0.045 in my table. And if I look that up, I know it needs to be negative because it's on the left. 0.04, 0.045, where are we at? Right, so there's 0.0455. Is that as good as we're going to get? So this is 0.005 away, and this is 0.004 away, so that's a little bit closer. So minus 1.7 will be the value that is closest to 0.045. All right, so that is the value that has 0.045 underneath. So minus 1.7. Okay, minus 1.7. But it's two-tailed, so we need both tails. And because it's symmetric, okay, this is going to be the negative version, this is going to be the positive version. So that's 1.7. And so when we conduct our tests, we will compute the test value. If the test value falls down here, or if it falls up here, then we will be rejecting our null hypothesis. Right? So that's the procedures that we're going to go through. Right? So stepwise, so we're going to start out, we're going to state our hypotheses, we'll identify our claim, we'll find our critical values from the appropriate table, and for our course we'll be using either the Z or the T table. We'll compute the test value, and then we'll take that test value and figure out, does it fall in the critical or the non-critical region? And depending on that, we'll then make our decision whether we reject or not reject our null hypothesis, and then we'll be summarizing our results. Right, so this is the overview of how the process is going to go. We'll take this process and we will apply it. So section 8.2 will be applying this to a Z test, and section 8.3 will be applying this to a T test. So right now it's important for you to start understanding how to set up your hypotheses, how to figure out identifying what your critical region would look like as far as one-tailed being left or right, and a two-tailed. And then once we start computing our actual test statistics, then that will help you follow through with completing the actual hypothesis test. And that will be after your break. So if you have any questions, send them my way, and I will see you after spring break. Have a good one.